Welcome, everyone. My name is Ricardo. I will be giving you today a talk that is an introduction to PDE modeling with a very simple example of boiling an egg. I am Ricardo. I work from the Mathematical Computation Group at Wolfram Research. And today's talk will be an introduction, as I said, to PDE modeling with the finite element method. And this is a kind of introductory talk. So if you're experiencing this, you might know one of few things that I will mention. But the goal is to give you an introduction with a very simple model. We will start by a very simple setup of our model, and we will iterate through several versions of the model that will be a bit more nuanced each time. So first, why use finite elements? The finite element method is very good when you are trying to solve PDEs in arbitrarily shaped regions. And it also solves for a very large class of partial differential equations. And to model with the finite element method, you need a discrete representation of the region that is what we call a mesh. You also need the partial differential equation itself, and you need the boundary conditions that link that equation to the region, and also that contain sometimes information about the physics of the problem you're trying to solve. If you would like an in-depth overview of this, you can go to this link in the documentation, or you can just paste it in the documentation center. And because we'll be modeling the boiling of the egg, we will like to compare to a real example of cooking an egg. So I took this chart from the internet. You can, if you're curious, you can click here. So that's what we will comparing with. And we will start with our first version. This first version is to get a workflow started. So we will like to keep in mind the size of the objects and the geometry and the units we will going to use. First, you need to load the finite element package, and also you can set history length to 0. If you're curious to what that does, you can click and see the documentation for yourself. But basically, it saves us a little bit of computational memory. And to start, we define a very simple region that is half a circle, and we define a circle, a line, and join them with region union, and that's our region. And a function that is very important and we will use a lot today is two-element mesh. You take that region and pass it through element mesh, and you get a mesh like this that you can visualize by calling wireframe like that. We will be working with axial symmetry and in cylindrical coordinates, so have that in mind. And you can build your PDE in general in the Wolfram language. You have tools that lets you build your PDE term by term with these PDE term functions. Or you can use, if you know what equation you are modeling, there are lots of PDE components, for instance, Schrödinger PDE component, Helmholtz PDE component that lets you build the equation from the parameters. For instance, you can define the reduced Planck constant or the mass of the particle you're wanting to model, and the Schrödinger PDE component will give you that equation, and you can look that in this link here. Because we want to model the temperature of the egg through time, we will use the heat transfer PDE component. And this will be the PDE, the equation that we want to solve today. As you can see, we have, for this case, two terms, the diffusion term and the term that describes the time evolution of the temperature. And we have three parameters that are very important: the conductivity, the heat capacity, and the density. And if you're rusty on the heat equation, you can click to this link and that give you a refresher on that. And because the heat transfer PD component uses SI-based units as default, we will stick with SI-based units. That's Kelvin for temperature, meters for the special variables, and the time in seconds. And we, to define our PD, we need parameters and variables. The variables are the dependent variable, time, and the spatial variables. And because this is a very simple model, this is our first version, we will just set the parameters as default, and we will only specify the region symmetry as axis symmetric, and that will give us the axis symmetric version of our model like that. We will also need boundary conditions. The initial temperature, we will consider an egg that is at room temperature. So we define the initial temperature, the initial condition like that. And then we need to worry about the boundary condition temperature. So for this, we need them to be consistent with one another. The process of putting the egg into the boiling water and the physics of it is that the contact of the water with the egg, we will model through the boundary condition. So we would like a boundary condition that sets the temperature at 100 degrees in the outside of the egg. The problem is that we already have set the initial temperature to room temperature. So there is a mismatch there at the boundary. So what we will do is define a boundary function that will start at the room temperature and very quickly get up to the boiling temperature of the water in around 1/10 of a second. That will model the process of putting the egg in the water. And to define the boundary condition, it could be as simple as defining the temperature equal to that boundary function, and with this equation would be where that's true. So that will be the outside of the egg. That's fine, and that's very simple, and that's okay, but we will do something slightly different, and it consists on first visualizing the element markers of the boundary of the mesh. So we can see that outside the egg, the elements are 3 and 2, and at the axis of symmetry, the markers are equal to 1. So we define with this function heat temperature condition, the element marker, if they are different to 1, then the surface temperature is that of that boundary function that we defined. And if you're curious of how to visualize this mesh, you can look to this tutorial here that is linked here. And we also need a symmetry boundary condition because this is an axial symmetric model. And we do that with heat symmetry value. And that basically returns a Neumann zero value, but in this case, where the element marker is equal to 1, okay? If you need a refresher on Neumann values, you can click these 2 links, and that will explain to you what's a Neumann value and how to use it and why to use it in the finite element method context. We define a simple arbitrary end time for our simulation, and then we use NDSolve, which basically implements that finite element method for us, okay? We specified with this first argument, we have our operator. This is our PDE that we defined earlier, and we equate that to the symmetry condition or any Neumann values we have. But if we don't have that, then we just set that to 0. And then the boundary condition, initial conditions, the dependent variable in this case is T. Then the range of the time, and here is very, very important that we here pass the mesh and say that the spatial variables belong to that region, to the mesh. So that basically tells the spatial discretization that the NDSolve will use is based on that mesh. Then our solution is simply an interpolating function. You can evaluate that interpolating function at time 0, at half the radius, or at c equal to 0, for instance, and that will give you the temperature of that point at that time, okay? If you call values and grid, you get the whole values of the solution, and you can calculate the minimum and maximum values. To do that more simply, we here define an offset, and that offset will help us transform that minimum and maximum values to degrees Celsius to be more readable. So, and we can, for instance, make a contour plot of that solution at a particular time, and we get our plot. But we would like to make an animation. So for that, we make a helper function called temperature contour plot. Here are a bunch of options for that plot, but basically we are plotting that solution with the ranges of temperature defined here, and showing that along with the edge frame of the mesh. We can do that the exact same for a different plot, for density plot. That is the one we will use here. We define frames and map that function that depends on our solution to the number of frames and the range of times we want to visualize. And we can see that right here. So this is a very boring solution. It basically heats up very quickly up to 100 degrees. Nothing very profound there, but this is just to set up the model. We know that we don't have any errors, and we know that our model is at least showing something. For the next version, what we will do is to get a ballpark of some kind of realistic parameters, okay? So mass density, heat capacity, and thermal conductivity. We redefine those parameters and also redefine the end time to 10 minutes for the simulation time. That will give us a different PDE, and we can solve it in exactly the same way. But we get something really, really weird here. We are getting a negative temperature. That doesn't make any sense, that you put an egg in boiling water and it gets cold. So to inspect that, we take the solution and see at where is the minimum value, get that position, and from the time steps it takes that you can extract from the solution, you can get what is the time that occurs. And if we plot the solution at that particular time, problematic time, we can see that you get lots of oscillations near the boundary, okay? Lots of oscillations there. And you can also visualize that along with the element mesh. And you can see that here there are only like 3 elements to approximate that sharp transition, because again, we have 100 degrees at the outside and 20 degrees in the inside. So that is a very sharp transition. And in this image, that few elements in the boundary cannot approximate very well that solution. So we get undershoots and overshoots. So to do that, we will use an option for 2-element mesh called mesh refinement function. And that refinement function, we could, because we have this region, we could define a region and assign region distance and define that refinement function as a function of that distance. If you plot it like this, you can see that it gets very low as you get closer to the edge of the egg. And we define the refinement function like this, depending on that sign distance function. And you can visualize now the new mesh that is refined. We can then solve it once again, but with a monitor, an evaluation monitor, because since the mesh is now refined, it will take a little bit more time, so it's useful to do that. And we now get a very nice range of temperatures that makes more sense. Then we can define the frames, rasterize them if you want, and visualize them right here. And we get a nice solution heating of the egg from the outside through the inside, okay? If we inspect the temperature at the center of the egg at 6 minutes, you can see that there is around 40 degrees Celsius. So that's seems a bit too low. So let's keep refining the model. In this next version, we will represent two regions because we have the yolk and the egg white, okay? So for that, I simply define a new circle with an inner radius, and I join them, and I get my new region. We also will define these parameters for the egg yolk and for the egg white to differentiate them, these material regions. So here in the two-element mesh, now I will use this option region marker that will let me define differentiate between the material region of the yolk and the material region of the white. Okay. So now my mesh looks like this. But since I changed it, I need to visualize the element markers again. And now I see that the element markers in the outside are either 5 here in this corner or 2. So I define that in my boundary condition function. Then I pass that, I use the refinement function to the mesh, and I get my refined new mesh with 2 regions this time. And based on this paper, we can define the mass density for both the egg yolk and the egg white, and the same for the thermal conductivity and specific heat capacity. That way, we get a different PDE. In this case, you can see that the coefficients depend on our piecewise functions, and we solve the PDE exactly the same way with ND-solve. We get a reasonable range of temperatures. It's always good to check that. And in our simulation, we can see something very similar. So, but when we inspect the temperature at the center of the egg at 6 minutes, we see that now we get an even lower temperature there. So something is not quite right yet. And we can refine that model further. And for that, we can think about the heat capacity, conductivity, and density. These are quantities that might depend also on temperature. So we can now model what happens when we consider the changes in temperature, in density, heat capacity, and all of that with temperature itself. So it will become a nonlinear model in which the coefficients of our PDE depend itself on the dependent variable. So it would look like this. Now you have here the data for the density of both egg yolk and white. And we use interpolation to produce the interpolation from that experimental data in the range of temperatures that we want. And we do the same for the conductivity. These are based on the papers I cite a bit earlier. But we have a little bit less data for the heat capacity. So we, instead of interpolation, use linear fit model, and that will give us an equation that models linearly the dependence on temperature, just like this. So we now have these functions, and we redefine our parameters again as piecewise functions like before. And now our PDE looks like this. So you can see it's a bit more complicated. And this is a nonlinear model. It is normal for it to take a little bit more time. So we measure the memory used and the time it takes. And we get a reasonable ranges of temperature. And from this paper, we can also define 2 important things: the denaturation temperature of the white and the denaturation temperature of the yolk. And that will let us know if the egg is getting cooked or not. Okay, then we define this helper function for the plots. We define the frames, rasterize them, and here you can see that we're visualizing not only the time, the evolution of the temperature in time, but also the green contour is for the denaturation temperature of the white, and the magenta contour is for the denaturation temperature of the yolk. So if we look, for instance, at 6 minutes, we see that the whole yolk, the whole white has surpassed its denaturation temperature, which is good. It seems that it's cooked by then. But if we look at 10 minutes, for instance, we see that not the whole egg is cooked because some part of the egg yolk has not surpassed that denaturation temperature. So there is something off there. And because at 10 minutes, we are supposed to have a fully cooked egg. If we inspect the temperature at the center at 6 minutes, we see that it's very low. It's compared to the denaturation temperature of the yolk. So we need to refine the model further. To do that, in this case, from this paper, we take this expression that defines the geometry of the egg that depends on these 3 parameters that you can inspect yourself. We define a spline, and we define a region with that spline, and we get a new region. We define our mesh, and we inspect the element markers to see if we can use the same boundary condition. And as we can see, we have the same element markers as before, so we can still use that boundary condition. But the problem is that the refinement function is no longer useful because we define that for a circle. So here, if you consider a point in the mesh, and we would like to define, this is just an option, but we would like to define the refinement based on the green distance from that point to the shell. So if we take a function that gives us the point in the shell as a function of c, and then take that function and subtract the value of r, that will be the blue one, you get that distance in green that we can plot here, but we can also plot it cubed, and it will become decrease very rapidly. Then we can define the refinement function as a function of that distance cubed with an offset, and redefine our new mesh. This is a trial and error process, just so you know. And we get our new refined mesh. We solve it. It takes a little bit more time. We get reasonable ranges of temperature, nothing crazy there. And now we can see that the whole egg is cooked at 10 minutes. And if we look at 6 minutes, the whole white is cooked, but also the center of the egg, the yolk, is still not cooked, so it's still runny, which is something that we expect from this chart. We can see that the temperature at the center is nearly 60 degrees, which is good. And now we are in the position of using our model to make some predictions. So here we will, let's consider a new initial condition of 8 degrees Celsius. That would be an egg that is taken straight out of the fridge. And we solve the problem in the exact same way, but now we have solution fridge, and we have a different ratio of values, and we can also visualize that solution. The problem is that we cannot really compare with this density plot. So we define 2 more helper functions that will let us visualize also the denaturation for the solution and for the solution with the egg taken out of the fridge. So to compare those results. And here you can see first that at time 6 times, the temperature for the refrigerated egg is a little bit lower than the room temperature egg. That makes sense. And also you can see that at 6 minutes, the room temperature egg is a bit more cooked inside the yolk, where the refrigerated egg is the yolk is completely runny still. So if you like an egg that is completely runny, you can cook it for 6 minutes and use a refrigerated egg. But if you like, for instance, eggs cool cooked all the way through, then if you're using a refrigerated egg, 8 minutes might be, sorry, if you're using a room temperature egg, 8 minutes might be enough. But if you're using a refrigerated egg, on the other hand, you need to wait a little bit past that 8 minutes mark, okay? So some conclusions. Creating a simple version first and then building up your model is very useful step by step. Also, sharp transitions in the solution variables can cause numerical instability, and you can refine the mesh accordingly for your needs. And also, it's very useful to have a way to compare your results with the real world and also incorporate real data into your model, as we did. If you're curious and want to play with this yourself, you will get these slides soon enough. Here is my email if you need any questions. And also you can click this to go to the full model of the egg that is on the documentation. And there are more examples than I was able to show here. Thank you very much.